Good afternoon, everyone. My name is Yexin Xiao. I come from Zhejiang University. The topic of the oral presentation is numerical study of the combustion flow characteristics in a hydrogen-filled cavity-based scramjet combustor. We will go through these 4 parts. And first, a brief introduction. You can see from this picture that is a cavity-based scramjet combustor. You can see the flame extinction process and the reignition process. Ignition and extinction processes are common in supersonic combustion. The local flame structure deviates significantly from the quasi-steady laminar flame, making flamelet class models unreliable for calculation. And in this case, a finite reaction chemistry model may be more useful. As a standard FRC model, partially stirred reactor model is widely used in scramjet calculation. It takes into account the turbulent mixing timescale and the chemistry timescale, and is simple and efficient. Although widely used, the PSR model still has many problems in actual supersonic combustion flow simulations. Some people compare the results of the unsteady PSR model and the compressibility correction. And other people point out that there are large differences between the calculation results using different chemistry timescale schemes, especially when considering the differences between the species distributions. And some people studied the effect of turbulent mixing timescale on supersonic hydrogen injection combustion. And the turbulent mixing timescale will affect the combustion rate, and the flame temperature will be different. And some people found in the posterior calculation process that the calculation schemes of both the chemistry timescale and the turbulent mixing timescale are particularly important under medium to high color weight number. Some people studied the combination of different chemistry timescale and turbulent mixing timescales, and you can see from this picture the timescale here varies greatly. The legend here in this case is range from this is about millisecond to second, and here is about microsecond to milliseconds, and the mixing timescale here is also. So our study is to propose an improved chemistry timescale calculation scheme based on the Fox PSR model, and compare it with other computational schemes and experimental measurements. Here is the numerical methods. Multi-species reaction flow Navier-Stokes equations are selected. And the calculation in this study adopts the delayed detached eddy simulation based on the Sparta-Armors one equation range model and the PSR turbulent combustion model. Also, the 7-species 8-step simplified chemistry reaction mechanism is selected. Here is the spatial discretization and the temporal discretization. We use round method here to the spatial discretization and reconstruction, and one-order Euler method for temporal discretization. The model assumption of the PSR model is based on the eddy dissipation concept model. In this calculation, the control volume is divided into fine structure and surrounding structure. And also the reaction rate can be also composed of these 2 parts. The reaction rate of the fine structure and the reaction rate of the surrounding structure. And sometimes we can just think this part is equal to 0 and can get this formula. And the gamma here is the volume friction of the fine structure, and you can calculate it by this equation. And in this work, the geometric mean timescale scheme is used to calculate the turbulent mixing timescale, including the Kolmogorov eddy dissipation timescale and the eddy stretching timescale. Multiple chemistry timescale calculation schemes were used for calculation, including the former open-form scheme and the later open-form scheme. This equation was used before open-form V10, and this was used after that. Meanwhile, the slowest chemistry formation timescale also used in here. It's calculated by this equation. The new computational model we used is called improved individual PSR model. The chemistry timescale is calculated for each reaction equation, and the PSR correction is applied to each reaction equation too. You can see the gamma R, the subscribe R here is denotes the reaction R, and use this equation to calculate the total reaction rate. And here is the calculation model and the working condition. The computational model used to validate the PSR results is a hydrogen-filled cavity-based scramjet combustor. And the calculation simulated the Mach number 4.0 flight condition. The isolation selection inflow parameters and fuel injection parameters are shown here. In order to verify the model results, the simulation results with fuel equivalence ratios of 0.1 and 0.3 were calculated. And the model mesh contains about 6 million cells. The characteristic size of the cells is shown here. And here is the wall pressure distribution along the flow path. You can see from when the EQR here denotes to the equivalence ratio. When it is a low EQR case, the four schemes almost get the acceptable pressure distribution here. And when it comes to a high EQR case, the former form scheme showed a significant high pressure here, and which means that it significantly overestimated the heat release of the reaction. And the slowest formation timescale commonly used in our study and the later form scheme are consistent with the experiment in low EQR case. However, they are also significantly higher than the experiment in this case. Here is a flame image and the flame image from the experiment and the time average temperature field in calculation. And there's no significant difference in the time average temperature field here, except the PSR form odd. Because you can see this area, the flame spread beyond the cavity. Spread beyond the cavity. Here is a Schlieren image from experiment and the density gradient field from calculations. So little difference here. And this is the OHPD from experiment, and here is the OH distribution results. You can see they are quite different because in the calculation, the OH concentrates on the real wall of the cavity. Almost all the methods are failed here. And here is the flame image for high EQR case. There's no significant difference. Here is a Schirren image for high EQR case. However, you can see this shock just behind the injection, and for these two cases, you can merely see this shock. And here is the OHP leaf for high EQR case. And this time, the IIPSR is in good agreement with the experiment, since in other case the OH almost fulfills the cavity. And here is the chemistry timescale calculation by these three schemes. You can see these two schemes have little differences. The color here is deeper, which means the chemistry timescale here is smaller than the old one. And the slowest formation timescale here is significantly different from these two, because you can see this green light here. It may be caused by the shock wave, but doesn't mean anything to combustion. And here is the DA number analysis. It is a DA Q dot diagram, and this is calculated in the IIPSR calculation, and the chemistry timescale here is the minimum chemistry consumption timescale, and these two diagrams show almost the same concentration here from DA number from 1 to 100, but there are still some different, because you can see these two diagrams, there is a slight rightward shift here, which this area has more points. And the purpose of this new PS model is to currently simulate the instability of the supersonic combustion. And actually, we have used this to solve the low frequency instability in cavity-based scramjet and get some results. If we use the form scheme, we only get a stable flame. Okay. You see the flame flashback and the extinction process. Here we come to the conclusions. At low equivalence ratio, almost all schemes can produce acceptable stable flame results, although there are some inconsistencies in the species distribution. However, at high equivalence ratios, the pressure result of other schemes show huge distinction from the experimental results. At the same time, the species distribution and shock train structure are also different from the experiment. Our new PSR model performs well in both high and low equivalence ratio calculations. And under high equivalence ratios, the DAQ dot result exhibits a slight rightward shift, indicating that the combustion gradually transforms from mixing dominated to reaction dominated.